This application is generically asking this man, when was your last pregnancy? The appropriate answer for him is NA or non-applicable. We may come across a situation where we have to answer NA or non-applicable because we don't want to or cannot accurately answer that question. We leave it blank. In most programming languages, when we don't want to assign a value to a variable because it is an unknown or unanswerable, it is called null. In this code, we have a myAgeInt, which was set to 30. The yourAgeInt has not been filled in yet. What's going to happen when we try to run this code? We will get an error since we can't use an unassigned variable to a write line. To show that we didn't forget this is really a null, we're going to explicitly assign it a null. That way the console.writeLine is going to be happy. But this will cause an error during the initialization because integers normally do not allow nulls. This is because integers are a value type. Integers must have a value. By putting a question mark right after the int keyword for the data type, it will now allow nulls, and this program will run. Both write lines will run. The first write line will display 30, and the next write line will display a null. The question mark was a shorthand for this notation, which makes the int nullable. Let's start off by creating the Working with Nulls project. Let's declare two nullable bytes. Byte question mark, called byte-one for byte 1, and byte question mark, byte-two, which is the name byte 2. Let's set byte 1 to be equal to 30. And let's set byte 2 to be equal to null. Perfectly valid since they're nullable types. Now, let's write them out to the screen. Console.writeLine, byte 1, which will be the value of byte-one, and console.writeLine, values for byte 2, which is the variable byte-two. Let's pause it at the end with a console.read key. Let's run and test the code. Notice it says byte 1 30 and it says byte 2 because it doesn't have anything as it's null. So we see byte 1 has a value, byte 2 does not have a value. Let's do a console write line and just say whether or not they have a value. Let's copy these two write lines down below. Now, byte 1 dot has value and byte 2 dot has value. Let's run this. Notice it says byte 1 has value is true. Byte 2 has value is false. Let's set the byte 2 variable so it's no longer null and set it to 25. Now we can see byte 1 is 30, byte 2 is 25, and they're both true on has value. We might think we don't have to make these byte variables nullable anymore because they both have values. When we run this, we get an error. You know why? Non-nullable types always have a value. So non-nullable types do not have this has value property. The only way a byte instance would have the has value property is if it's nullable. Let's look at casting between null and non-nullable types. Let's create a brand new console application and call it null casting. In here, let's create an integer, and it's a nullable integer called x, but we won't make it null. We will actually set it to 10, which is a valid integer value. And we'll make another integer called y, which is equal to x, and this is a not nullable type. Let's see if we can run this program. The reason we get an error is because it cannot implicitly convert a nullable int into a regular int. Why? An int nullable is actually larger. Think about this. If an int can go from negative 2.1 billion to positive 2.1 billion, including 0, And so can the nullable int, plus the nullable int has one more value that the int doesn't have. It has null. So the nullable int has more combinations than the regular int, and you can't guarantee that it's always going to implicitly cast. Well, we know this is going to work because it's 10, and 10 will fit into an int. So we just simply typecast that. And now this program will run. Time for Lab 4.3, Skill Check 1. Take a moment to pause this video and challenge yourself to do this skill check. And that does it for Lab 4.3 on Nullable Types. Our next item, Lab 5.1, If Else.